Okay, this is going to be our only video or our only presentation, class presentation for week 5. Subject is data and information security. That is broadly defined a well-informed sense or assurance that the information risks and controls are in balance. A little provocative quote to ponder right there. Comes down to the old notion of preparation, being prepared. The whole idea of security and communication and transmission goes back not just to World War II, which is kind of represented by this code machine here, but even earlier. The concept of passwords, secret coded information and communications, and being able to keep your information private predates the computer era. This is a German code machine, and if you want to take some time to read the caption there, it relates to uh, coding and the code breakers of World War II. We won't dwell on that right now. Computer security, actual computer security, began after the first mainframes were developed, uh, and after World War II really created the first modern computers and rudimentary computer networks. Physical controls were required to limit access to personnel, and there were only rudimentary controls available at the time. It really got going and really became important maybe 10 or 20 years later, actually in the 60s, with the Department of Defense and their ARPA project. This was the entity that actually led to the emergence a number of decades later of the internet. But ARPA began examining the feasibility of redundant network computer systems and computer communication systems. And that was originally intended, as a lot of you guys probably know, as a military concept to link military installations and NASA and codes and all those other things. So there's some military history underpinning the internet, underpinning computer technology, and the whole notion of security. This I won't read to you, but it's available if you want to pause and look at it. It's kind of an overview of what ARPA was all about. ARPANET grew in popularity, as did potential for misuse. There were problems with it. There was no safety procedure in place for what were then dial-up connections using phone lines, or nor for user identification and authorization. And that wasn't really necessary, though, because in the late 70s, the microprocessor industry, computers were really kind of uh, a newly born thing where a lot of people weren't on networks. I can remember in my first job, a lot of us had computers. I didn't, but a lot of us did, and ultimately I myself did. We had individual computers where we just basically carried floppy disks back and forth and around. They weren't networked together. We weren't using email at that point in time. All that started to change rather quickly, though. The RAND report was the first major government-sponsored report that looked into the scope and importance of computer and data security, not just the safety of the data, but limiting access and making it really a management priority. So computers and networks and computers became more and more common, and they became more and more interconnected. First, we had inter-office connected computers. Gradually, the world of retail moved to a world where we weren't using mechanical cash registers, but registers connected to central processing centers. There were services, online communication services like CompuServe and AOL, America Online, which is still around in kind of another form. And these were making the first kind of global manifestation of computer networks. I don't even think, and this is probably going back to the early 90s, We didn't really start calling it the internet until as I think pointed out in an earlier presentation, until the mid-90s. Security was even then a low priority. Since then, we've all lost phones, we've all had computers crash, we've all had maybe some of us have had breaches and seen charges on our debit or credit cards that we didn't authorize. So power outages have caused data to be lost, files to be lost, entire hard drives have. I've actually lost an entire hard drive one time. So that's all part of security. It's not just hackers, it's physical security too. Today, the internet has millions of us connected. Obviously, the internet makes this course possible, right? Many are unsecured. Most established networks, however, do offer their own measures of security to kind of protect from users and to protect users from the network. So, plus there are many services that you're familiar with, like Norton, antivirus, Symantec. There's a lot of built-in security in the Windows 10 systems now. In fact, a lot of times they tell you to not even use some of the older Windows systems just because of security issues. Macs are a little safer from a security standpoint, but not 100% so. So information security is kind of the art or the state of science to be free from danger. To be protected from the adversaries, a successful organization needs to have physical security, operation security, communication security, and network security. So we have to protect information and elements such as the systems and hardware that use, store, and transmit the information. And this involves policy, general awareness, public information, that sort of thing, training, education, and constant improvements in technology, obviously. So leave it to the CIA to be involved in something like this, right? So the CIA triangle was a standard based on three things: confidentiality, integrity, and availability. In other words, keeping information secure between people and agencies and individuals and users and that sort of thing. Protecting the information, in other words, not allowing it to degrade, deteriorate, get compromised, fall victim to natural disaster. And then availability, have it accessible to people. So the CIA triangle has expanded into a list of critical characteristics that are kind of the hallmarks of information security. Those are basically availability, accuracy, authenticity, confidentiality, again, integrity, utility, and possession. Here they are kind of diagrammed in both 2D and 3D, particularly confidentiality, integrity, and availability. The cube, that Rubik's Cube looking thing over on the right, basically is designed to get everyone to take a kind of full dimensional view of everything involved in the triangle. And the whole policy, education, technology thing is designed to apply to everything. So I guess you can kind of look at it as a Rubik's Cube. Here is your general diagram of a hacker versus the hackee. This is, obviously, there are several types of loss or threat to any network or any computer or any information asset. The one is the malicious actor, the hacker or the cracker, as he may be called. And basically that's a diagram. Computer as a subject of an attack. You can focus on that at your leisure if you so choose. So the whole thing is about balancing security and access. It's actually, as we know, and we're all probably well aware from hard lessons, it's impossible to obtain perfect security. It's not an absolute, it's a process. It needs to be kind of a balance between protection and availability. Protection obviously is the security, some of the things we talked about, but also it has to be available. Anything on a computer is not useful to anybody if it can't be accessed when needed for the purposes it was intended. So to achieve balance, the level of security must always allow reasonable access, yet protect against threats. Threats can be a number of things, as we saw in the one video. Hopefully you guys have already seen that. If not, pay attention to the section where we talk about the threats being in a kind of a continuum. Here's another grid-like thing to look at, between non-malicious and malicious. What would a non-malicious threat be? Probably the computer going down because of a power failure, or maybe you lose your keyboard because you spilled a drink on it. I've actually lost an entire laptop that way. All the way to malicious, which is the hacker or the cracker or somebody, an alien government as far as the Department of Defense would be concerned. And they range from harmless to catastrophic. So my spilling a drink on my laptop was kind of non-malicious. I didn't intend to do that, but it ended up being, it was not completely catastrophic, but it cost me about $700. So, in other words, the information on the hard drive was ultimately saved, but I had to have a new microprocessor put in. I mean, that's kind of a crude little personal example, but I think it helps clarify things. Moving away from a personal example to a more system-wide or corporate level, security is basically a two-lane highway, you could say. There's the top-down approach and the bottom-up approach. And these are just what they say they are. In other words, the need or the initiative in security is harbored in both of those directions and anywhere in between. The bottoms-up approach is kind of the grassroots effort, the people that work with systems, network administrators, security people, end users even in a university or corporate setting. These are all considered the people that might initiate things from the bottom up. A key advantage is the technical expertise of the people actually kind of on the front line. Does lack critical features, including participant support, or organizational endorsement, and staying power. These things can emerge, but as I say, they're more grassroots in the way they start out. The top-down approach are security initiatives, policy, procedures, and processes that come from upper management. And these are ultimately things that dictate goals and expected outcomes in any security improvement project or any project really to eliminate threat. A main goal here is to generate accountability for every action and every approach. Obviously, with strong upper management support, things are a lot easier for the people down below. I don't mean down below in terms of status or stature or organizational positioning, but in terms of actually working with the problems. As I say, the grassroots, the front line. A lot of organizations are engaged in various forms of what's known as a systems development life cycle. That's basically a management system. It's kind of a paradigm, a diagrammed methodology that you'll see here. And it kind of takes a full view of the process. Basically, as you see here, these kind of little semicircular loops. And it kind of works in a top-down, bottom-up way as you look at it. Investigation, analysis, design from a logical standpoint and a physical standpoint, implementation, and then maintenance and change. And like all good loop systems, remember we were talking about systems last week, there is a kind of a continual process, or the system never dies, so to speak. So this is kind of another way of applying systems to security. important. There is a variant to the SDLC process known as the SEC-SDLC. The SEC there is, I think, representative of the word security, and that basically means that it's more of a priority. Whereas in the standard SDLC process, the focus is on design and implementation of an information system. SDLC involves identifying specific threats and the risk that they represent to the system or to the network, and puts an emphasis on controls to counter, mitigate, and manage risk. So anyway, the phases of the SDLC diagram we saw a second ago are investigation. We see here some of the components of those, the processes, statement of program policy, the kinds of things that you get in any organizational initiative, the teams and the processes around those, all of those, remember from last week, systems, and organizational feasibility. Analysis is analysis, the kinds of things we always associate with that concept. The logical and the physical design. Here again, we get to the element of systems and the processes, the hardware, the software, the networking that goes into that. Blueprints, planning, the security, consultants, meeting with teams, that sort of thing, and then ultimately feasibility studies. Implementation, obviously, solutions are acquired, personnel are assigned. There's obviously testing. I always think it's interesting to see the different ways organizations handle things. And that's always part of these processes. I also teach classes at Marist College, and I know their IT system is somewhat different than CUCA colleges. Just for example, I've been involved with CUCA since I think 2013, and I was assigned a password, and I still have the same password. At Marist, they enable you to choose your password within certain parameters, and which is all well and good, but you have to change it every 6 months or you get thrown off the system and you have to make application with IT to get reinstated. So it's a mess, or it's a potential mess if you don't do it. So anyway, two different approaches. At some point, that practice was the output of these kinds of SDLC examinations and implementations. So maintenance and change, obviously, is what it sounds like. And here we are, we're back to the bottom level, right? The users, the network administrators, the people on networks all having input. So again, a second look, kind of top down and bottom up. Investigation, analysis, logical design, physical design, implementation, maintenance, and change. Kind of, if we look at it from a systems perspective, it should be autopoiesis, right? Remembering from last week. Is security an art or a science? Here we have kind of a clip or a screen cut from one of the videos we saw where the whole notions of art and the ancient castles in the medieval period, they made an art of security really by using natural barriers and systems of moats and drawbridges, folks up in the turrets with arrows, bows and arrows, I'm sure, passwords. I don't know, if somebody finally got up the cliff and across the drawbridge, the people standing at the gate would say, "Password, please," and you would have to say something, "May Queen Matilda live forever," or something like that. A more scientific approach is kind of demonstrated over here in the left, modern era, multi-layered security, but it's still, if you look at the way the diagram is laid out, it still has elements of the castle system, right? So With the level of complexity in today's information systems, implementation has kind of got to be a combination of art and science. Art means there are no hard, fast rules, nor are there, excuse me, many universally accepted solutions. If there was a magical user's manual, then everyone would be using it and everyone would be doing the same thing. But because there are all different organizations and different human beings, uh, you know, there has to be different approaches and new challenges will emerge. Things will happen in this arena that we haven't even worried about or thought about yet. It's a science too. Security is definitely a science dealing with technology. You have to understand that virtually all actions occur in computer systems, and when they do occur, they bring about faults, security holes, malfunctions. A lot of times we hear about new systems that are released, and then we hear about security patches. Well, that's a result of needing to repair or account for things that weren't considered. In other words, bringing systems thinking into play. And security is a bit of a social science, right? We have to deal with the behavior of individuals interacting with systems. Uh, People ultimately are what's reflected in the systems, in the technology, and in the use and application of those systems. Uh, we're often thought of as possibly the weakest link in the security chain, human beings, right? Yet we human beings are the ones that design and administrate such things. So that's all for this week.